As always, I'm going to share my screen and going to be writing things on Notability for you. I'll start by reviewing the notes from last lecture. So here we go. So last lecture was my sort of next attempt to try to connect this class and the material we learn in this class to the physical world. And my hope is that you are at least to some extent familiar with op amps. They're a very, very practical piece of electronic instrumentation that you know, if you're building anything in the analog world, you're likely to use an op amp as part of that. So yeah, so what I'm doing is I'm connecting what we're learning about to sort of being able to come up with op amp representations. And mainly what I'm doing, I mean, I explained the theory or the sort of the perspective that we use when we talk about op amps. You know, the virtual ground at the input. This isn't the only configuration you can have for an op amp. So there are other ways in which this could be constructed, but this is a, you know, the inverting amplifier is certainly one of the very common configurations that you would use for that. And we could talk about other amplifier configurations too, but I think that would unnecessarily confuse our discussion. But because of this point here, this point where we have this virtual ground, this point here, we're able to get this incredible behavior where we can have an input coming in and an output going out and be able to see the relationships between those very directly, and then using just the components that we talked about in not the last lecture, but the lecture before, where we talked about capacitors, inductors, and resistors. We can pretty much make up all of this kind of behavior. And then after the simple P amplifier, then the summing junction. The summing junction is very important, and I will show you that in today's lecture, how and why it's so very important. And then we started to look at integrators and differentiators, how simple the configuration was for that, then more sophisticated PI or PD controllers, and then we started to sort of deal with more complicated controllers like this simple lag controller, but it has lots of control within it, so you can change CF, RI, or RF. So you have a lot of variability that sort of becomes available to you with this. And then we didn't talk about PID, but we talked about phase lead and phase lag controllers, which have very similar behaviors to PID controllers. And they don't have the issue of wind up and realizability that PID controllers can have. So we can basically put this RC combination both on the input side and the output side, and based upon what values we put in for R and C and F and RI and CI, we can get, you know, a wide range of behaviors from these systems. Okay, so I think that's where we ended up, and I'm sure you're still saying, how is this connecting? I mean, you see that we can build up interesting transfer functions here, but you're still wondering, how does this connect to this class? But hopefully in the next few minutes, you'll see how it connects. Are there any questions about any of this that we have talked about in this lecture? Then before I actually go to that, it crossed my mind that, do I have assignment 2 here? I don't have it in front of me. Curses. Okay, let me see if I can just find it somewhere. Assignment 2B, there we are. Okay. So I want to make sure that we're all good on what's expected. I had a couple of questions on assignment 2 from students, and probably a good idea to just talk about it. Unfortunately, as I say, I don't have it available in Notability here, so I can't really talk about it directly in front of you like that. But so for question one, essentially you're given a feedback system with you know, two forward components. You know, there's s+2 divided by s+3 divided by s+5 multiplied by 10. That's going forward, and then there's a feedback element which has got a 0.1 associated with it. You're asked to determine what the transient response is. So transient response is the response that essentially decays away, and that transient response is due not to any input from RFS, but it's due to the initial values. So what you're supposed to do for this question is you're supposed to determine what the closed loop transfer function is. So that's the transfer function, input-output relationship, right? Then what you need to do is you need to say, wait a minute, we're looking for the, somebody's talking. Hello. All right. So what we're looking for is that input-output relationship, but the input is going to be 0. So you have to take the transfer function, break it up into one part that multiplies CFS and one part that multiplies RFS, and then make RFS equal to 0. So then it's CFS multiplied by a polynomial is equal to 0. And then what you want to do is you really want to go back into the time domain and then say, okay, I'm going to calculate the Laplace transform of this, but I'm going to include initial values. So everywhere where there's an s squared term, you're going to add minus s c at 0, and then a c dot at 0. Anywhere there's an s, you're going to add a c. You're going to subtract a c0 from that, and you're going to modify that equation, and it's still all equal to 0. Then you move the parts to the right-hand side that are due to these non-C based terms, and then you're gonna calculate the inverse Laplace transform of that with the initial values for C0 for C0 and C dot 0 as indicated, so -1 and 2, and you're going to come up with the transient response. So that's what you have to do for question 1. For question 2, I've given you the pole 0 plot, and then I say, what if this thing is excited by a ramp function? So a ramp function is 1 over s squared in the Laplace domain. So you want to include that, and then you essentially want to take the terms that you can see from the pole 0 plot and create the transfer function for that. Okay, and then you're essentially, all you're doing is what's the output, so you just want to write that as a function of s, and that's what's expected in question 2. In question 3, I'm giving you sort of the easy graphical problem where the poles and zeros are all on the real axis. So you need to draw vectors for the residues for each of the poles. For the polynomials that are given, you're given the whole system. There's no feedback or anything else. You're just given the function, and you want to come up with the step response for this. So the step response means the unit step, that you have to do the S transform for that. That's multiplying GFS. As they say, you're going to come up with the graphical representation of the system. You're going to come up with the residues, and then write out the did I ask for the time domain? Yeah, find the step response. So we want the time domain response of this thing, right? For question number 3. And question number 4, it says find the response. So what I mean by find the response, it's actually the total response of the system when it's excited by a unit step and it has initial conditions. So what you have to do is you have to say, okay, it's being excited by a unit step, so that's the transfer function. I'm going to come up with the S domain. Well, you're going to come up with the S domain representation, and then come up with the time domain representation for that unit step. And then you're going to say, okay, I want to come up with the initial conditions, the impact of the initial conditions, and I'm going to keep the unit step to, like, I'm going to have no input, and I'm going to figure out what the response of the system to those initial conditions are going to be. And then my total response is the sum of the response from the unit step plus the response due to the initial conditions, and that's going to give you the total response. So that's what I'm looking for in question number 4.
Sorry, so we use those initial conditions after we bring it back to the time domain?
Well, sort of, yes, but you really don't need to go into the time domain. You can just look at anytime there's an S squared, you know what's going to happen, right?
Right.
You're going to add a S multiplied by C at 0, right? Or subtract that, and then you're going to subtract a derivative of C, like C dot at 0, right? That's what you're going to do for a single S,
Right.
for an S squared, right?
Right.
Like, I mean, officially what you do is you go back into the time domain and calculate the Laplace transform, including initial conditions. But you can go directly from one to the other.
Okay, sounds good.
Okay.
Can you just go over the Q1 stuff as well after? Or the question 1 stuff? I missed just like the part of it, or
you mean halfway. You were not on time for my class? Oh my God. All right, question 1. Yeah, so for question 1, we have a transfer, well, you have a flow diagram, right? Or flow chart, right? What you want to do is you want to calculate the closed loop response, or determine what the closed loop transfer function for the system is going to be. Once you do that, then you split it up so that you take part of the polynomial in the denominator, multiply that to S. The numerator polynomial is multiplying R. Then you say R is equal to 0. Then you need to go from this transfer function sort of version of this to sort of the time domain version, and then deal with the initial conditions. But you don't really need to go into the time domain. Anytime there's an S squared, you're going to have those additional S and first derivative terms coming up, and all those terms, they're going to have to be injected into what you're doing, right? And then you stick in the initial conditions, move everything other than C onto the right hand side, and then calculate the inverse transform.
All right, thanks a bunch. Yeah.
So for question 1, I want the time domain value, right? For question 2, I don't need the time domain. It's just what's the signals S domain output signals S domain representation. Okay. Got it?
Yeah. Thank you.
Yeah. Because that's a little bit ugly, if I remember correctly, to go into the time domain. That one for number 2.
Okay, yeah. Thanks for the heads up on that.
And number 3, as I say, is just a very
your mic's been cut, I think.
Yeah, we can't hear you.
Yeah.
Have you been hearing me?
No.
Oh,
We can hear you now, though.
Yeah, you kind of at the very start after you finished talking about.
Oh,
Welcome back.
From there, it was just
Yeah.
dead silence.
really?
Yeah, sorry about that.
Nobody sent me a chat. Nobody did anything.
No,
There were
you weren't
stuff in the
not
chat.
in. You were not in the room
What?
at all.
I wasn't in the room.
You disconnected.
No.
That's why
You left the
even
meeting,
said it.
yeah.
Oh my God! This beautiful lecture I gave. Oh no! Alright. We were chatting in the chat. Even
Yeah, we were all
okay.
talking too. We were waiting for you to come back.
I had no idea that I was off. Okay.
Jeez.
All right. Well, let's see what I wrote. Here we go. Screen. Start broadcast.
Did you figure we were just ignoring you or something?
Yeah, just being super quiet because it's real confusing.
That's funny.
Okay. So, did you see any of this?
Nope.
Oh my
We didn't-
God.
I'm sorry.
Okay.
Yeah, like
When you left, someone
Yeah.
said that you left, but
Yeah.
we didn't get any reply.
I think you finished talking about the assignment and then it just cut directly
And then
after
it
that.
cut, hey?
So probably right when you started downloading
Oh
the title.
God, that's so horrible. Okay, so now I'll just talk about this, right? So we're now continuing on with our taking sort of math and re-representing it as you know, op amps, components, that sort of a thing. So the example is one of taking a differential equation and re-representing it using op amps. So we consider this equation here, which is x double dot plus 6x dot plus 22x is equal to r, right? That's an input-output relationship, right? Somebody say right.
Right.
Okay, good. Sorry, I'm going to keep doing that now because that was awful. All right. So then the first step we have to turning this differential equation, which is an input-output relationship, turning this relationship into an op amp is we reorganize the equation to solve for the highest derivative term. So there was an x double dot in the equation. So now we're solving for x double dot. Right? So x double dot is equal to negative 6x dot minus 22x plus r. Okay, so why did we do this? Why did we solve for x double dot? Well, the basic structure that we're going to use is we're going to use the summing junction, right? So back in the previous lecture, we had a summing junction, right? So we want to add up all these elements, all these terms in that differential equation. So we'll use something like this, where you got R1 times, RF divided by R1 times whatever is coming in, all these things. And remember, there's minus signs actually associated with each one of these terms, right? Because this is a differential amplifier, so it has a sign inversion. So we're gonna try to come up with each of these terms, right? I'll underline them. So there's one term here. There's one term here that's a 6x dot. There's another term which is 22x, and then there's the r. Now notice also the r has got a plus sign associated with it, and all these other terms have got minus signs associated with it, right? Now the summing junction essentially is inverting. So we're going to feed a minus r into the summing junction, and it's just got, like, there's no coefficient in front of the r, so we're going to put a 1 and a 1 here, so there's no gain associated with it. It's just going to be a summing junction. So now we need to incorporate the minus 6 dot and the minus 22x term into the summer. So in this example, also on top of that, in this example, and in general, I recommend that you use only integral forms, summers, and gain terms, okay? So you'll see what I mean as we go through this. So I just duplicated this minus R going into this amplifier with 1 1 in it. So that's let me change colors. That's this part here, right? I got that. And what I say is that the output of this is going to be X. The output of this is going to be X double dot, right? So if it's X double dot and I need this term 6X dot, how am I going to get that? Well, as I said, we're going to use integrators, right? So in order to use an integrator, what we have to do is we have to feed back with a capacitor. And in this case, I put a 0.2 and a 1 for the capacitor. So that gives me a gain of 5. There's a sign reversal, and this is an integrator. So X double dot turns into X dot with a gain of 5, or a gain of minus 5, actually. So from this thing, we are now going to be able to, this thing being X double dot, we're going to generate minus 5X dot, right? And then we can take the minus 5X dot and run it through another integrator, which has got a capacitor and a resistor, but both these values are 1. So I'm going to get an integration, which is going to change the sign, and it's going to integrate it. So it was minus 5X dot, it becomes plus 5X. So those are the components I need. Because I need to create a term with an X dot in it and a term with an X in it. And now I have a minus 5X dot and a plus 5X that I have generated from this thing, which is my X double dot, right? So from X double dot, I generated minus 5X dot, and I generated 5X. So now I don't want minus 5, I want minus 6, but since my summing junction changes the sign, I'm actually going to need plus 6. So what I do here is I create just a sign reversal. So it's a buffer which changes sign. So we got a 1 and we got a 1 here, and they're resistors. So I get plus 5X dot coming out of that. Let me erase these things now. So I got a plus 5X dot coming out of this amplifier here, okay? I feed that into a voltage divider. The voltage divider gives me 0.6 of the 5X dot. So that means I get 0.6 of 5X dot is 3 times X dot, okay? Then I can run it through an amplifier, right? The summing junction can amplify. So if I put a 0.5 as the input resistor, the feedback resistor is still 1. So 0.5 dividing into 1 gives me a gain of 2. So the 3 will become a minus 6. And that is what I need. I need a minus 6. So I have the R and I have the minus 6 now, right? The R is over here. I have the minus 6 coming through this thing. Then what I do is I need to create the 22X. So I have 5X here, but I need 22X, okay? So I put it through, again, a voltage divider here, which is 22 over 25. So the 5X gets knocked down to 22 divided by 5X, because this is just a voltage divider, right? So now it's scaled down, but it's 22 over 5, but I need minus 22. So I need to get rid of that divide by 5. So I put in a 0.2 ohm resistor here, and my feedback resistor is 1. So 1 divided by 0.2 gives me 5, multiplying 22 over 5, which gives me 22, minus 22 coming back, and that's what I need here. All right. So that's how I generate this differential equation using op amps, integrators, summing junctions, that sort of a thing. All right, who followed me?
Like partially, but I'm just confused about some of the terms. Is that Are those all like point resistors that you have, like in like 0.5, 0.2, and 0.2 in front of the op amps?
Yeah, these are just this is 0.2 ohms here, for example.
Oh,
right?
They're all less than 1. Yeah. Oh, okay. Thanks.
Right. This is actually a voltage divider, right? So this guy I could implement like this, right? So if I put 3 ohms here, and then I have an output and 22 ohms here, right? If my input goes this way, then my output is going to be 22 over, like, that's how I will implement this thing. So if I have a little circle like this, essentially all I'm doing is knocking down these circles can't have any gain associated with them. To have gain, I need an op amp. Okay. But these are voltage dividers. So this guy is also a voltage divider here, right? 0.6. All right. Anyway, so what I can do is I can take this differential input-output relationship that I had, and first step is to solve for the highest differential or the highest derivative term. Throw everything else onto the other side. Then each term of what's on the other side is going to just be going through this summing junction here, right? I'm building up a summing junction through the summer. I have a minus R going in there. I have a 3x going into it, but the summer for this branch is a gain of 2. And then I have a 22 over x coming through this branch, but the summer has a gain of 5, so the 5 disappears. And they're all sign reversal. The summing junction is sign reversal. That's why I put a minus R in, so that I got a plus R coming out. I put a plus 5 in, plus 5 x or plus 3x in, and I get a minus 6 out because the gain and the sign reversal of the summing junction. So every part of this differential equation I can implement. And the funny thing, or the confusing thing, is that there's lots of ways. I didn't have to do all this stuff. I could have just incorporated other things into the coefficients here, and if I'd have done that, I may not have needed everything that I put in below. But the idea is to sort of show you all the things that I can do or that are available to me just with these 3 things, right? Which is integral, summers, and gain terms. Okay, that's all I'm using, and I can implement, or I can realize this differential equation or this input-output relationship, which is captured by this differential equation. Okay.
So when you're using coefficients and you're choosing them, is it pretty much just trial and error and then you adjust as you go along, or is there some system that you're following to pick your coefficients?
Well, right now it's not trial and error, but there is really no system, right? We're not really constrained by not having particular components, right? Like, I mean, for instance, I'm putting a 1 farad capacitor here, right? You don't often have 1 farad capacitors, right? But you don't, like, you could pick some other value of resistor so that we would still get a gain of 5, for example, right? But what I was trying to do was show you sort of the capabilities, right? So the capability here is one of getting a gain of 5, like in this part of it, a gain of 5, but there is a sign reversal too, which is kind of a problem because I'm going to get a second sign reversal through this summing junction, right? So I need to put a buffer in which changes the sign one more time here with these things, right? With these things, I changed the sign one more time. So I had a minus 5, it became a plus 5. Then I dropped it down to, with a 0.6 voltage divider, to turn it into 3x dot, and then I gave it a gain of 2 in the summing junction. So I'm just kind of showing you the flexibility you have, but you don't need to have you don't need to have all these different things happening. right? We could probably implement this equation with less components, this equation here. Really we're implementing this equation here, but we recast it as the sum of a bunch of terms to give you the highest derivative component, and then we use a summing junction. Do you all see the summing junction? Yes, no?
Could you possibly circle it?
Sure. Well, let me do this. I'll first show you in the previous lecture, right? I had the summing junction here, right? Remember how I had all these terms coming in? Because this is a virtual ground, all these currents just basically flow like this, right? So because this is a virtual ground, nothing does this, right? That doesn't happen because there's no way that for it to come back up, right? So they all just flow through this, and so that like, as I say, a bunch of resistors feeding into a single point with a single feedback resistor. That's what we have here, right? Like, so the summer is all of this, right? Well, let me keep that one maybe. Undo. The summer is all of this, right? That's my summing sort of piece in this thing, right? Where I have a bunch of inputs. So one input, I don't know why I have this arrow going this way. So one input is going from R, another input is going through here, and a third input is going through here, right? So all these inputs are going into the summing junction. The summing junction is an inverting junction. That's why I put a minus R in and a plus R, which is what I want. Then I have a minus 6 I need to get. I have a plus 3. So the summing junction for this branch has a gain of 2. So the minus the 3x dot turns into like gets a gain of minus 2, so it turns into a minus 6, right? Does that make sense? Somebody asked me a question about this.
Where does the x double dot come from?
Well, the x double dot is what we're going to make everything equal to. The x double dot is the sum of all these parts, right? So we just say, I assume that I'm going to generate an x double dot right here. If it were an x double dot, then running through an integrator, I would get an x dot here. If this were an x dot, then I would get an x here, right?
Okay.
And I make up the x double dot by building up all these chunks, all these terms through a summing junction. So it doesn't start out when I draw it as x dot because I just drew the first part, right? Like the r minus r going into the summing junction. But then by feeding back all the other terms, I built it up and created, as I say, I built it up with all these other terms. I built it up and made it into x double dot.
Okay.
So when you draw this, what you have to do is you have to say, okay, my input, I'm going to put into a summing junction, and my output, I'm going to say is going to be x double dot. Then I'm going to integrate x double dot to give me x dot, and then integrate x dot to give me x, feed that back, use the summing junction, and lo and behold, I will have it x double dot. Okay?
And you got that 5 with the 0.2 resistor.
That's right. I got a gain of 5 because I got a 0.2 going in, and I got the feedback resistor, which is 1. So 1 divided by 0.2 gives me 5. And I multiplied that to the input, which is 22 over 5. So I blew away the 5 in the denominator and created negative 22, which is what I needed. Right? But I mean, I'm really sort of being stupid in the sense of Why did I create 5x here? I could have just created 22x right off the bat and not had any of this garbage, right? If I didn't want to put this here, I could have eliminated it by picking appropriate resistors here and here. But I included it like this so that you sort of see how I can manipulate and modify things. Right? I needed to feed back minus 22. I generated 5x instead of 22. Then I took 5x and ran it through this voltage divider to give me 22 over 5. And then I had in my summer a gain of 5 to get rid of the 5 in the denominator to give me minus 22x, which is what I needed here. So I'm doing a bunch of things that I don't need to do, but I'm doing those things so that you sort of see the choices or the tools that are available to you. I'm going to get rid of this and these things because they'll just confuse ultimately. Right? I'm putting all that here so that you sort of see how this can be created. Right? Like, what are all the tools that are sort of available to you? We got 3 inputs that we need to generate. We need to create, right? This one, and this one. How did we get to this point? We took our differential equation and solved for the highest derivative term and said, okay, now I need to add up all these guys in order to create that highest derivative term, right? And I said, my input comes in, okay? I'm allowed to feed in minus R or R, right? Either of those are fine. So if this had a minus sign associated with it, then I would have fed R in directly. But since this has got a plus sign associated with it, I fed in minus R, okay? All the rest of the signs I managed by either putting inverting amplifiers in or not, right? Like there's an extra inverting amplifier that I've put in here, right? This is a extra inverting amplifier. It has no gain, it just changes the sign. So we went from minus 5x dot to plus 5x dot with that inverting amplifier. It's kind of a, I mean, you need to change the sign, but all this other stuff I could have incorporated into the gain of these elements, but I never did. Okay? But again, what I'm trying to do is make this real. Trying to make this such that you could say, okay, I have this relationship. I'm assuming that my little greenhouse has so much energy coming in. That's my R. It's got so much loss. There's some other things, a fan running, whatever that is, right? I can capture, model all of that, and here's the differential relationship, and here's how I can implement those terms, right? And now I can understand how I should adjust
We can't hear you again, or at least I can't.
Yeah. Same boat.
Yeah,
You can't
it's out.
either.
I don't think he can hear us either.
Yeah, me either. He's still it's still his he's still like in charge of it though, isn't he?
That's what it shows.
Yeah, it looks like he's still connected through his iPad.
Interesting. Oh, now he's gone.
Right.
Well,
Tell
this
me
is
we had a way to actually contact him.
Yeah.
I'm
you
just
can
sending
email
an email about the notes.
Yeah, if he could post today's notes, that'd be money.
Hello.
Yeah, you're finally back.
Oh, you're back.
Yeah,
Yeah.
you're back.
This is awful. What's going on? So when did I fade out again?
It was about 4 or 5 minutes ago. Ooh, maybe less.
Lord.
Probably less than that, maybe.
Like
Okay.
I think
Yeah.
you're wrapping up the explanation on that big,
On that
messy,
top one,
messy
right?
circuit.
So
Yeah, the big
the
one.
next thing I said was, okay, suppose let's see if you're on track. So what if I had this differential equation? What do you suggest I do next if I want to implement it?
Yeah, I don't think we heard that
We
part.
can't see.
Okay.
Also,
now
we
you're
can't
hearing
we can't see your screen as well.
it. You cannot see my screen.
No.
Okay. Share content. How long has that been going on?
Since you left, I think.
Yeah,
Just
I
the
think
5
your
minutes
audio.
ago.
I think the audio cut out before
The screen cut out.
the screen cut out.
Okay, you see my screen now.
Yeah, that's back.
Yeah. Yeah.
This is really terrible today's lecture. Okay. So what I was asking was what would you do with this now? How would you implement this?
Oh, take the highest derivative out. Solve for that first.
Okay. So tell me what to write.
X dot of t equals to
Yeah.
I guess RT minus minus 5xt over, and then all of them would be over 3.
Well, here let's make it separate. So
Or yeah, just separate.
right? Need to change the angle. Are you still here? Because maybe it's my turning. Are you still there?
Yeah, we can hear you.
Okay, because I thought maybe because it's a iPad, and when I'm switching it around, maybe. Okay, so that's good, right? So that way I can write a little bit better too. Okay, so now what would we do next? So we are going to create a summing junction, right?
Yeah.
So we would take R, right? R is coming in, and we need to divide it to create like it's divided by 3, right? So we would just take this and run it into something like that, right? 0.33, right? And then into a resistor 1. And that's my summing junction, right? I'm starting. So the value here is going to be what? Like not what it is right now, but what do we want it to be?
X dot.
X dot. Very good. Right? So if it's X dot, how do I get to how do I make that X dot? Well, I feed this term back in, right? So how do I make that term? How do I make an X out of X dot?
Could I integrate the circuit?
Yeah, so I'm going to have an integration, right? So I'm going to integrate this thing, right? I'm going to integrate this thing. And so if I'm feeding this back, right, what values will I use in order to create? So I want to have, what I want to have is a 5/3x at this point here, right? How would I get that?
Well,
What would I?
Would you just do like the 0.33 kind of similarity where you did for the R?
Well, yeah, and a little bit different though, right? So here, basically, if I put a 5 here and a 3 here, I would get that, right? Because it's the fed back term divided by the input term, right? Now, this is X dot, so I would actually get a minus 5/3x dot, right? X here, right? That makes sense?
Yep.
Okay. Now I'm going to feed this into the summing junction here, right? So what I have to do is I have to bring this back. Now, if I look at my equation, I'm feeding, I have an R divided by 3, right? This thing actually changes the sign, so I need to put a minus R in, and the summing junction is going to change the sign, right? Right?
Yeah.
Right? So that's why I put a minus R in. Now here, I already have a minus 5/3, but it's going to have its sign changed. So I actually need to change the sign one more time. So I'm going to take this and I'm going to run it through a resistor, have a junction like this, and feed this back like this and go 1, 1. And now I have 5/3x, right?
With your connection at the first resistor, wouldn't it be like after how you did it up in the equation above?
Yeah, I put it in the wrong spot.
Okay.
Hang on. Let me just see here. No, this is still okay, right? These are just the various lines coming in. So this is fine. This is going to go like this. And it's now going to go into a resistor here. So this was a gain of 1. This is going to have a gain of what? 1 again, right? Right? So so this gives me the second term, right? This is now a 5/3x, right? That's what I have here, right? And here what I have is a minus R/3 term here, right? And my summing junction is only going to be inverting the signal, so the minus R/3 becomes plus R/3. That's this term here, right? And the 5/3x goes through the summing junction and becomes minus 5/3x, right? Does that make sense?
So can you just explain a little bit on why the number, like the 1 ohm resistor on the bottom right hand of the circuit, of the whole circuit, why
this guy?
No, the other one to the right.
Oh, here, this one, yeah.
Yeah, so why is that? Why is the circuit splitting before that rather than after that, like the other ones?
Oh, because I drew it wrong.
Oh, okay, no worries.
Oops. That's what happens when you do things on the fly.
And sorry, what's the use of the resistor past that circuit?
This guy?
Yeah.
This is part, so this is part of our summing junction, right? So,
like based on that previous thing.
Yeah, you
Gotcha,
remember
gotcha.
how
Yeah.
each one of the R1, R2, R3? So, yeah, that's basically why we have that,
Okay,
that resistor there.
Makes sense.
Okay. All right, good. So see here, like what I did was I did the smarter thing, right? Like I just said, oh, I need 5/3, right? Here I did something crazy where I took it and I gave myself, 5x, right? Like I created this minus 5x dot, right? But I did that because I wanted to just play with some variations, right? But if I just want to build it exactly, I would just do this. You see what I'm saying? So there's more than one way to build this circuit, and this is a more efficient example than this one, but this doesn't show you all the variations that might be, required at some point. Does that make sense? Are you guys there?
Yeah.
Yeah, we're here.
All right. Well, this has been kind of a disjoint lecture. I'm sorry.
No worries.
Anyway. All right. So I think we'll stop there. Yeah.
Did you post these
we'll talk
notes?
on Friday. Oh, yeah. So I'm asking Keegan, and I don't know yet, but I'm asking Keegan if I can have a shot in the lab to do a quiz with you on 27 and 28. Okay? You should be able to see your marks. Somebody send me an email if you can't see your marks. Okay. And on the oral quizzes, and remember, I give you either 100%, three, like 4 out of 4, 3 out of 4, 2 out of 4, or 1 out of 4, right? So in general, you either got 100%, 75%, 50%, or 25%. Okay. And yes.
Oh, sorry. I think a lot of us have midterms in that week.
Do you not want it then?
If it's possible, could we shift it to either before or after, like that week?
Okay, let me talk to Keegan. Keegan is very slow replying to me. So is that generally the consensus? You'd rather have it? Then I would go with 19 and 20. I think the consensus is you'd rather not have it that week, right?
It would be, for me, it would be best if we did it like the first week of November, because I'm loaded up the week of the 19th and the week of the 26th for midterm.
Yeah, I'm wanting to have 3 exams if possible, because although I'm not saying this yet, what I want to do is I want to throw out one of the 3.
Oh, okay. I see.
Because you see, maybe you have a bad day. I don't want this to be, catastrophic for you. But I'm not saying that yet because I want to be able to have 3 exams. So that's why I kind of would like to have one in October and one in November. And the term ends right away in December, right? Like I think 5th of December or something. We have like 1 class in December and that's it.
Okay. Yeah, the 27, 28 would be better than for me personally, just because I've got like 3 midterms on the week of the 19th. So.
Okay.
So it's and then I got another one kind of on the 28th as well, same day as the lab for me. So it's busy. That's all.
Yeah. Well, okay. I mean, send me emails and I'm good with whatever the group wants, but I'd like to try to have an oral quiz in October if possible, and then we can have one in November. And if we have 3, then I'm good with dumping the lower mark in one of those 3 quizzes. Okay?
What some of the professors have been doing is that you can have like a quiz and then just take the most results, like have your set of dates that are most comfortable to you, and then just have us all pick them, and then you'll get a feedback of the response or something like that, maybe. That might be easier than like 100 emails. I'm just trying to play it
Make it easier, right? Well, I'm hoping you guys will sort of talk amongst yourselves somehow, or you, like, many of you are in the same classes, so there should be a general consensus. Like, well, okay, let's just do it live right now. So which is better? Like some people have said the week of 26 is worse than the week of 19. Which in general, why don't you just tell me what you think?
Yeah, I think the week of the 21st would be the best.
Yeah.
The week of the 26th.
21st. I think that's what Matt said.
Yeah, I know, but
that's the same week.
Oh, yeah.
So the week of the 19th.
The earlier 19th. One, week of 19.
Yeah. That's what they're referring to.
That would work best for me as well.
And there's one poor guy who's got 3 exams that week, right?
A bunch of people just said in the chat the 27th is better for them.
Like around 7 of them.
Oh man, chat. There's 14 chats. Okay. Lord, what are we gonna do?
Are you just thinking there's another 1 question thing again, or?
Yeah, it'll just be the 1 question, 10 minutes. 10 minutes for 2 students. Yeah,
so
just
then,
like before, but remember the complexity of the questions will keep getting a little, more and more challenging because we've covered off more stuff. But see, I sort of feel like, I talk to you about the questions, so it becomes sort of a educational thing also, like you sort of see how to do the question as a result of the conversation. I think 27 seems like it's winning. More people are saying 27.
Either way, do you have any idea when the labs are going to start? I'm worried that Keegan is just going to dump a bunch of labs on us at the end of the semester.
Yeah. I saw Keegan. I talked to him. I know he's doing the best he can, but he's got this 280 class with 100 and, I don't know, 20 odd students, so he's kind of stressed by that. I can send him another email. When I sent him the last email, I sort of said the students really would like to know what the plan is. I CC'd Dr. LaForge, who's the program chair. I just don't know what to I'll ask him again to tell us what the plan is, because I don't know either what the plan is for labs.
Yeah, like what happened over 380 last summer there was we ended up doing 4 labs, a lab quiz, and a group project within the span of 2 to 3 weeks. And it was, and we actually had a little bit of an extension given to us where we didn't get a penalty, but it was in the week of all of our final exams, so we didn't really get an extension, and it was terrible.
That week sucked. It wasn't fun.
Yeah.
So it'd be best if if we could start.
Yeah. Okay. I'll pursue it. I'll talk to Keegan. I'll talk to Dr. LaForge, and we'll come up with a schedule for you as soon as possible. Okay.
Oh yeah. Thank you.
Also,
okay, thank you.
There's been a lot of back and forth about that ProTrack or whatever it is that's supposed to spy on you while you're writing the exams. So, wanting to avoid controversy, I'm going to go with the take-home exam. Okay? So you won't have to worry about Big Brother watching you. Okay?
Thanks.
Thank you.
You say that, but you'll hate me later when you see the exam. But yeah, no problem. I think it's best because I think it's still unclear what's acceptable and what's not. So why go that way? All it means is that I can give you a take-home exam. I think that works fine. But take-home exams tend to be a little bit challenging. So that's the bottom line. Anyway, all right, really good. We gone long enough.
I just had one last thing. Could you post today's lecture notes?
I'm generally against posting notes. Maybe I will. Today was kind of a disaster.
Thank you.
Yeah, I'll post it. No problem. All right, really good. Thanks a lot, guys. See you.